Hello everyone. In this lecture we will discuss about the equilibrium conversion of dinitrogen tetra oxide into nitrogen dioxide in the equilibrium reactor. So we will discuss the equilibrium conversion of uh, nitrogen tetroxide into nitrogen dioxide in equilibrium reactor. So we will, in the previous lecture we discussed the spin hysis. Now in this lecture we will discuss the equilibrium reaction in the DWSIM. So DWSIM, we will discuss the equilibrium reaction in the DWSIM software. So DWSIM software, this is lecture number 2. This is lecture number 2. In this lecture the dinitrogen tetroxide is converted into the nitrogen dioxide. This is equilibrium reaction. 1 mole of dinitrogen tetroxide gives us 2 mole of nitrogen dioxide, and this is the equilibrium reaction between nitrogen tetroxide and nitrogen dioxide. The feed consists of pure dinitrogen tetroxide. The temperature of the feed is 240 Kelvin and the pressure of the feed stream is 2 atmospheric pressure. This is the equilibrium reactor. The pressure drop across the reactor is 0, and this reactor is isothermal reactor. So the equilibrium constant for this reaction is 0.1 mole per dm cube, and the rate constant of dinitrogen tetroxide in this reaction is 0.5 per minute. So what will be the equilibrium conversion for this equilibrium reaction in this equilibrium reactor? So we will discuss this equilibrium conversion in the DWSIM software. We will also discuss this is as we know that this is a isothermal reactor, so the feed temperature will be equal to the product temperature, and the product temperature will be also equal to 240 Kelvin. This reaction will take place in the gaseous phase. So this is a gas phase reaction. All the components are in the gas or vapor phase. So we will go to the DWSIM. So we will open the DWSIM software. This is the DWSIM software. We will go to create. So create, click on create. So click on create, and it will take. So now click on next and add component. So there are two component: dinitrogen tetroxide, dinitrogen tetra oxide. So it is N2O4, nitrogen tetra oxide. So click on this one, and now add the other component, nitrogen dioxide. Nitrogen dioxide. This is the nitrogen dioxide, NO2. So click on next and add the property package. So from the property package we will go to the Finn-Robinson equation of state. So we will go to the Finn-Robinson PR, and we will click on add. So this is added. Now we will go now click on next, and in the unit of system we will select C5. So click on C5 and click on finish. Now this is the material stream and this is the energy stream. So I'm drag the material stream, double click. This is the feed stream, so I'm double click on this one. So this is the feed stream. I will give name to it. This is the feed stream, and the temperature of the feed stream given in the question is that the temperature of the feed stream is 240 Kelvin and 2 atmospheric pressure is the pressure. So 240 Kelvin, 240 Kelvin, 240 Kelvin, 240 Kelvin, and the pressure is 2 atmospheric pressure, 2 atm, 2 atm. So 2 atm is the pressure, and the molar flow rate in the question, that the molar flow rate of nitrogen tetra oxide is 100 kilogram mole per hour. So 100 kilogram mole per hour, kilogram mole, we will go to the molar flow rate, 100 kilogram mole per 100 kilogram, 100 kilomole per hour. Enter it the value, all we will enter all the values in the DWSIM. So now this is the feed stream, its value is color change from red to blue, so it means it is fully specified. The feed stream is fully specified. Now we will go to the reactor. In the reactor we will go to the equilibrium reactor. So drag the equilibrium reactor. This is the equilibrium reactor. Now this is the equilibrium reactor, and this is 3 is the wafer. This is the wafer or the top product. So in the top there is are gases. So gases, top gases, top product gases, and this is the bottom liquid. So click on the bottom, which is enter it, and this is the energy stream. This is the energy stream. So I will, this is the energy, E1 is the energy, so I'm changing its name to energy, enter it. So the energy. Now the top product, this is the temperature, and this is the bottom product. Now click on the reactor. So in the reactor name is given, but it is equilibrium reactor. So this is the equilibrium reactor. This is the equilibrium reactor. The feed, the connection stream, the inlet stream is the feed, the outlet stream one is are the top gases, and the stream number 2 is the bottom liquid, and this stream is the energy. This is the energy stream. So all the stream are connected to the reactor. Now I will add the reaction set to this equilibrium reactor. So I will go to setting. So click on setting. In the setting, this window will open. So in this is thermodynamic reaction. Click on reaction and go to the reaction, chemical reaction. Click on this one. This is the equilibrium reaction. So click on equilibrium and add the reaction. So nitrogen tetroxide and nitrogen dioxide. So all the components are included in the reaction, and the basic component is the nitrogen tetroxide. The stoichiometric coefficient of nitrogen tetroxide, this is the reactant. So we will put -1, and the nitrogen 2 mole of nitrogen dioxide, and 2 will be positive because nitrogen dioxide is the product. The stoichiometric coefficient for the product will be positive, and for reactant it will be negative. So this is balance, and this is the balance equation, and the phase, all the components are in the gaseous phase. So I will put enter the wafer value. The minimum temperature is 0 Kelvin and maximum is 2000 Kelvin. So I will put the minimum temperature to minus 200 Kelvin. So I will put it minus 200 Kelvin, and the maximum temperature will be 2000. and the temperature approached, and this is the basis is the fugacity. So this is I will look this is okay, fugacity, and this is the equilibrium constant. So it can be calculated from the Gibbs free energy, and it can be calculated from the equilibrium constant can be calculated from the uh, temperature function, and its constant value, that value can be constant. So the equilibrium constant value is given in the question. So the equilibrium constant value is given, it is equilibrium constant is 0.1 mole per dm cube. So its value is 0.1 mole per dm cube. So its value is 0.1 mole per dm cube. 0.1 mole per dm cube. So I will click on, now click on OK. So I will click on OK, and this is the mole per dm cube, the equilibrium constant value. So click on OK. So now close this window and double click on the reactor. Double click on the reactor. So double click on the reactor, and this is the reaction set. So go to the reaction, and this is the default, and in the reaction set go to the parameter and click on the default, and this is the isothermal reactor. So in the isothermal condition, this is the isothermal reactor, the feed and product temperature are constant. So in this menu I will go to the isothermal. So now this is okay, this is okay. Now the equilibrium, I will go to the reactor to check the equilibrium conversion. So double click on the equilibrium reactor, and then go to the calculation parameter. We will go from the result, we will go to the reaction. So the reaction extent is this one, and the conversion is 65.76. so this is the equilibrium conversion of this reaction. We can also click on the top product. So the top temperature is this one, and the bottom temperature, and these are the bottom stream. So now for the adiabatic case is the top temperature and the bottom temperature. So this is the, now for the adiabatic case, if the reactor is in adiabatic case, this is isothermal. For isothermal reactor, for adiabatic reactor, this will be for the adiabatic reactor. So for the adiabatic reactor, the equilibrium conversion will be 65%, and for the isothermal reactor it will be 65.67, and click on solve. So it is 65% conversion, and for the adiabatic case it will be equal to 65.76, and for isothermal, so these are for the, this is the equilibrium conversion for the isothermal reactor is 65.76. Thank you very much for your attention. If you are new to the channel, please like and subscribe.